In this video, we're going to talk about rational functions, and we're going to kind of approach this from a more theoretical standpoint. So you probably worked with rational functions in a previous algebra class, especially if you did like intermediate algebra here in college. Um, but rational functions are when we are working with negative powers. That's how we end up with a rational exponent. So here's kind of a nice simple example of that. Let's say you plan to drive 100 miles. Find a formula for the trip. For the time the trip will take as a function of the speed you drive. So what we know is that we kind of have this idea when we're talking about driving and speeds and how long and time that we have what's called distance equals rate times time. In this case, we know the distance, it's 100 miles. What we don't know is the rate. And we're trying to think of this as what the time is going to be, knowing what the rate is for the trip. So in other words, they're trying to have us create an equation where we solve for t, which means I would divide by r on both sides. So t equals 100 divided by r. And we could think of this as a function, t of r equals 100 over r. Or another way of writing that would be 100 times r to the negative 1. So this just simple example demonstrates a rational function, the fact that it can be written as a fraction, and it really is represented as a negative exponent. Okay, so we kind of dive in a little bit on this. First, this type of an equation is called an inverse proportional relationship. You might have heard that before. That's when one quantity is divided by another, like in this example, y equals 5 over x. You might have heard of that in a previous class before. Also, we're really referring to some functions we've seen before, in particular the reciprocal function and the reciprocal squared function, the 1 over x and the 1 over x squared. Now, what we want to focus on both of these functions are what the book is going to refer to as short run behavior versus long run behavior, which we've heard of long run behavior. But short run behavior is the idea that interesting things are happening at specific numbers. So for the reciprocal function, the number that's interesting to us is when when x equals 0, we end up having this kind of interesting thing happening with the function where it doesn't end up crossing there. And that also happens with 1 over x squared at that same moment, right? At x equals 0, it doesn't end up crossing that point. That is what the book is going to refer to as short run behavior. And what we're seeing here is a vertical asymptote. And I believe I've used that terminology when I first introduced these functions. And you've probably seen this terminology at some point before. But if not, when we see a graph kind of approach a vertical line like this, where it doesn't want to cross, that's a vertical asymptote. In both of these graphs, the vertical asymptote is happening at the line x equals 0. X equals 0 represents the vertical line right there at x equals 0. So that's a vertical asymptote. Long run behavior is looking at what happens when we put large or very large values of x or very small values of x, meaning letting x going to positive and negative infinity. So we see in both cases that they are ending up getting closer and closer to the x-axis. In other words, the function is approaching 0. So this is what we call, a horizontal asymptote. And they sum up that information right down here. A vertical asymptote of a graph is when a vertical line, which we call x equals a, that happens when f of x happens to start going to positive or negative infinity. A horizontal asymptote happens when, as x is going to positive or negative infinity, f of x is approaching a value. So they're kind of opposites. In the first one, f of x is going to infinity, where in the second one, x is the one going to infinity. Okay, so using this notation, which is a little bit abstract, but it is something used in calculus, let's describe the long and short behavior for this. So let's start with long run behavior. For long run behavior, that means they're referring to when x is going to positive infinity. So when x goes to positive infinity, this graph is approaching f of x. So f of x is going to 0. I said it's approaching f of x. Wow. What I meant to say is that f of x is approaching 0. It's getting closer and closer to the x-axis. But that also happens when x is going to negative infinity. The exact same thing. F of x is going to 0. The short run behavior is occurring at 0. So as x is going towards 0, then we're seeing that f of x is going to positive infinity on both sides. They're both going up to positive infinity. If one side went to negative infinity, we'd put the plus or minus. But because they're both going to positive infinity, we can just leave it as just positive infinity there. All right, so let's go ahead and kind of put this into practice in an example. Let's sketch a graph of the reciprocal function. So the reciprocal function is 1 over x. Let me just write that down, that one. We're going to sketch a graph of this, shifted 2 units to the left and up 3 units. And then we're going to identify the vertical and horizontal asymptotes. Okay, so the original function, which is above, normally has a vertical asymptote at x equals 0. But if we're shifting this to the left 2, that means then our vertical asymptote is shifting right there. And I use a dashed line to represent my vertical asymptotes when I'm drawing them. Normally it has a horizontal asymptote at the x-axis, or y equals 0. But because that's going to shift up 3, that is then going to be my x-axis right there. All right. So the graph then is going to look exactly the same. It's going to go through 1, 1, and then normally it'd be at 1/2 at the next point and 1/2 at this point, and it's going to do something like this. And then over here, same idea. It's going to go at 1, 1. I'm pretending that's the new axis. And then at 1/2 here and 1/2 here. And there you go. I do like half arrows when I have vertical and horizontal asymptotes, just so I don't cross them, just to make an emphasis of it. So in this case, the vertical asymptote, which I'm just going to do VA to represent vertical asymptote, that's occurring at x equals -2. Horizontal asymptote, that's occurring at y equals 3. So those two shifts actually shifted the vertical and horizontal asymptotes. Normally they're at 0 and 0, x equals 0, y equals 0, but it ends up being at -2 and 3 based on those shifting. Now, really quick, I do want to write out what the function actually is, the equation of this function, okay? So the equation of the function, if I'm taking the 1 over x function and I'm shifting it left 2, that's going to be a +2 next to the x, and then up 3 means it's going to be a +3 on the outside. Now, if I were to take a moment and give this a common denominator, in other words, if I put 3 over 1 and then multiply by x plus 2 on top and bottom, that's going to give me 1 over x plus 2 plus, okay, so that 3 is going to distribute to be 3x plus 6 over x plus 2. So that actually combines to be 3x plus 7 over x plus 2. So what I have here at the end is equivalent to what I started with. This f of x right here with the +3 is the same thing as this f of x right here. Both of them have the x plus 2 in the denominator. It just doesn't have that separate 3 part. So they actually make mention of that. This result is what we consider the general form for a rational function. So they define a rational function basically to be the ratio of 2 polynomials, one in the numerator, one in the denominator, just so that it's a little bit simpler to look at than to have that +3 floating around on the outside. Okay, so they like to do an example, another example with a word problem, and we're going to kind of set this up. So a large mixing tank currently contains 100 gallons of water into which 5 pounds of sugar has been mixed. A tap will open, pouring 10 gallons per minute of water into the tank at the same time sugar is being poured into the tank at a rate of 1 pound per minute. Let's find the concentration of sugar in the tank after T minutes. So after some indeterminate amount of time, how much is actually in there? Okay, so let's start by breaking this up into two things. We have two things happening. We have water happening and sugar. So let's start by talking about water. So currently in the tank, it has 100 gallons. And then they're going to add 10 gallons every minute. So 10T, I'll just use T for time. Oh, they told us to use T, never mind. T for time. 10T then is representing how much is going to be added every minute. So in 2 minutes, it'd be 20, 3 minutes, 30. Okay, so that's how the water looks. The sugar is starting off with, it has 5 pounds of sugar already in it. And then they're going to add 1 pound per minute. So again, 1 times T. Of course, I don't have to put the 1 there. It could just be T. So here's the concentration then. The concentration of pounds per gallon. So that pounds per gallon is implying, sorry, let me highlight that. Pounds per gallon is implying that we're going to look at how much sugar is in the water. And in other words, it's going to be the sugar over the water, pounds per gallon. The per is implying that gallon is what we're dividing by. So the concentration then, let me write that out, is sugar amount over water. So for us, let's write C of T for concentration is 5 plus T, instead of 1T, I just put the T, over 100 plus 10T. And there's our equation that represents this scenario, which is another example of a very traditional rational function. The top one being a polynomial, right, of degree 1, the bottom one being another polynomial of degree 1. And that ratio of them makes this a rational function. In the next video, we'll go ahead and talk a little bit more about vertical and horizontal asymptotes and how to find them, not from the graph, but from the equation.